and good afternoon, everyone. So today I'm going to present, as Professor Jian already mentioned, I come from Daimler Trucks Innovation Center, India. So I've been working there for the last 12 years. Today I am working as a principal engineer, especially in the field of electric powertrain systems, and that's precisely what I would be discussing today. I have, most of my career, I have been working on electric vehicles for the last 8 to 9 years. I think since Daimler even started working on electric vehicles in its commercial segment, I was involved in the development of it. So I'm here to give you a gist of the OEM perspective. We've been seeing a lot of academic side, how components are designed. We just saw about integrated chargers. I think you've had several other sessions. But today I'm going to give you a piece of my mind from the OEM perspective. So I'm going to basically give you a very brief overview in the next 45 minutes, 50 minutes or so, to make you understand how typically an electric vehicle is designed from an OEM perspective. What are the prerequisites that are really required to design an EV from a powertrain perspective? Today I will be only focusing on the powertrain side because that's my area of expertise. And then what are the major systems? We've been hearing about a lot of systems. We've been hearing about charging systems, battery management. We've been talking about thermal management, high voltage and all that. So today I will be just taking you through these systems and overview so that everybody understands what is a system, what does it mean from an electric vehicle point of view, and then obviously the design of the components is a deeper story. So today's presentation, what does it set out to achieve is exactly that, understanding the prerequisites of an EV design. And today, because I'm personally working on a commercial vehicle segment, I would be taking a lot of examples from the commercial vehicle industry, which is like a truck and a bus kind of industry, which caters to like transportation or a passenger movement, not basically a personal car kind of industry, though you can extrapolate or intrapolate the results even to the passenger vehicle segment. So I'll be taking a lot of examples from the electric vehicles, commercial vehicle segment. The second point is an overview and a basic understanding of major EV powertrain systems. I just mentioned some of them. We'll be looking at what does each of these systems do in an EV, what is their prime role, what are the major components that come together and form these systems? And then what are the basic functionalities or the features of these powertrain systems? How are they important to a powertrain design? And then we would be talking about, when we talk about vehicle features, how are these vehicle features actually mapped to these systems and components? We all talk, whenever we go and go to a dealer shop and go to buy an electric vehicle or say a two-wheeler of sorts. So we always talk about a feature of sorts, right? Does this come with so-and-so features? So how do we actually relate these vehicle features to these systems and components, the end product? That's what we'll also be looking into. And then maybe a very high-level overview of how a design of powertrain components happens from a powertrain perspective. Very top level, obviously not the exact electrical design, but I'll be talking about what are the major factors that you take into account when you actually go and select some of these components, like say an HV battery or an electric motor for sorts. And then lastly, since I come from a typical software development and R&D kind of an organization where we do a lot of controller development, I would be also taking you through with one example maybe, how probably one of these features is actually developed and integrated onto a controller, and then finally how is it integrated onto the vehicle, just so that you all know how does it happen on the industry side. This is what I set out to achieve. Hopefully by the end of the sessions, at least the overview of a generic EV vehicle design would be clear to most of you. Okay, then I would start this presentation officially with a video which is quite special to me. I will explain that a little later. I hope the audio works. I'll just start it. Yeah, it's working.
Wir sind hier in Norwegen, im finnischen Lappland, direkt am Polarkreis. Und Sinn und Zweck der Proben, warum wir hier sind, wir fahren hier unter extremen Kältebedingungen. Insbesondere die Batterien, wir wollen noch testen hier bei tief in die Batterien. Das machen die Batterien. Wir gucken auf die elektrisch betriebenen Wellenaggregate, wir laden die Ströme
elektrische Heizsystem richtig ausgelegt haben. Eine Winde ist ein ganz wichtiger, eine ganz kritische Auslegungsfall für so einen Batteriebus. Hängt damit zusammen, dass wir ja nicht die Abwärme von einem Verbrennungsmotor haben, die wir nutzen können, sondern die Wärme in Phase selbst aus den Batterien heraus generieren müssen. Damit haben wir einen sehr viel höheren Energieverbrauch und den versuchen wir natürlich zu optimieren.
Und das weitere Probenschwerpunkt liegt darin, auf schlüpfrige und glatte Oberfläche die Fahrzeuge zu erproben.
Darüber hinaus noch die Abstimmung der fahrenden Regelsysteme gewährleisten, weil eben der elektrische Antriebsstrang doch deutlich anders ist als der konventionelle Triebstrang. Das heißt, die ganzen Fahrdynamik-Regelsysteme, ASR, ESP, auch ALS müssen hier spezifisch abgestimmt werden.
Ergebnisse, die wir hier auswarten, waren teilweise direkt online in die Software einprogrammiert. Wir bekommen am nächsten Morgen eine geänderte Software, sodass wir täglich den Reifegrad der Fahrzeuge verbessern.
Ja, als Fazit kann ich sagen, alles in allem sind wir mit den Ergebnissen hier sehr zufrieden. Das ist auch richtig so, denn Sicherheit und Zuverlässigkeit sind für uns höchste Priorität.
Okay, so the product that you just saw here is the electric Citaro, which is also what you see here. It was the first ever electric product from the commercial vehicle side from Daimler. It was the first electric commercial vehicle that came from Daimler. And I was very fortunate to be amongst the first people who was actually involved in the development of this e-Citaro. I was involved in the traction control development majorly. That's my area of expertise. So the idea of showing this video is so that you can all visualize how does it all come together at the end. What is the end product that the customer finally sees? So that's what we are trying to see here. So this testing, which generally happens in Rovaniemi in Finland, it happens at -30, -40 degrees, wherein the objective of this testing is to actually check several features like heating, like anti-slip regulation, traction control, ESP, some of these factors already spoken about by our project manager. And a lot of these times, there were, like we used to do an on-vehicle tuning. You had to parameterize the software right there because you see basically how the software behaves. And we had to make such rapid changes in the software that the next morning, that was one of the lines that was spoken here, the next morning we have to give that software, retest it, and probably it would work, it would not work, and then we go on with the iterations. So with this as a context, with this as a pretext, just keeping this end product in mind, let's see what are the powertrain design requisites for designing an end product like this. So obviously, when I have to design an electric vehicle such as this, for example, in this case, e-Citaro is a passenger car, passenger vehicle movement. Like it's used as, just like we have Volvo and BMTC buses running here. It's the prime source of transport in Germany and many parts of Europe. So obviously, the transport corporation came to Daimler and they said, see, we want you to make a vehicle which can possibly cater to this kind of application, right? So it has to move passengers from the depot, from bus stops, from A point to B point, okay? So they come to you with a very high level vehicle specifications. So that's where we start our powertrain design at. We get a very high level vehicle specification in terms of the target range. So this particular vehicle was supposed to meet around 150-200 kilometers of range in one single charge, right? So that's what is the initial spec we get. That's how we start our entire design with. So target range is the first thing. Second thing is we have to be very aware of what is the application we are going to use for. This was basically for passenger movement. So we have to, during our design, there have to be some key factors kept into account while keeping in view what is the application. Since passengers are involved, there is a reinforced, focus on the safety and the comfort of the passengers, since you are moving passengers from here and there. So if it would be an electric truck, for example, which is used for, say, a long haulage kind of application, or for moving, like, say, a crane operation of sorts, you would have a different type of application, and so the components would have to be designed a little differently. For example, maybe comfort is not the top priority here, but a major focus would have to be kept in how you design the electric motor. So it has to be a high power, high torque kind of a motor. So this is a very high level prerequisite that you have to keep in mind. So the range, we talk about the application, and then we come to operating conditions. So I just spoke about testing in Finland, in the winter scenarios. So similarly, you have to consider in what situation would you be running this particular vehicle at. So in a city like Bangalore, the temperature do not shift too much. So you would have you don't have to pay too much attention of basically tuning the HVAC or the heating ventilation system. But in cities like European cities, wherein you have extreme winters, probably moderate summers, you have to keep into account that during extreme winters, how would the different components be working? They have their operating range of their own. So we have to ensure that they continue working exactly the same in -35 or +25. So this is something that we have to keep in mind while designing a vehicle. The fourth part is the GVWR, or the gross vehicle weight. So this is definitely a very important factor. So this is the weight of the vehicle itself, including the complete payload. So the complete weight of the vehicle. So this would be important to actually do your range simulations and then decide what would be the energy consumption at the end of the day, and then use to possibly design a battery, right? So this is an important factor as well. The next is voltage level. We talk a lot about high voltage, and especially commercial vehicles, they operate at more than 400. So 400 is also getting redundant now. We are moving towards 800 and higher. So we are moving towards 1000 volts. So voltage level is definitely a key factor which will help you design various components for the powertrain. The next being performance. Performance either in terms of torque, power, or how basically different components actually work in different conditions would also be considered. The next being type of charging. We spoke a lot about charging, but a vehicle could have, like for example, the Metropolitan Corporation would have come, though I don't need an AC charging, I'm good with a DC fast charging. So we will only design a vehicle with a DC fast charging. But if they say, no, I want my vehicle to actually charge overnight in the depot, I'll just leave it at the end of the day. Driver leaves it at the end of the day, and next morning, the vehicle is completely charged up. So then you have to provide it with an AC charging support also. So accordingly, your charger that would be designed, or even the charge controller, which I will talk about later, would have to cater to DC as well as AC charging, right? The next part being dimensions. Obviously, this is again needed for range simulations, your frontal area, your complete, basically your range simulations and the energy consumption analysis would also be depending on the dimensions of the vehicle. And the next, and probably a very important factor being customer feature requests. So there could be some specific requests that the customer could come with. So there are some customers who come and say, I want the charging plug not to be only on the left side, but also on the right side. Because you could have an accessibility of a charging station either from your left side or the right side. So he would say, why don't you give me a port on both sides? So you would have to design the charging system in such a way so that the requests from both the ends are catered to. Maybe not at the same time, obviously, but then the control software has to be designed in such a way that input from here or input from here is handled properly. So these are very high level. There are millions such specifications that we have to look into when actually designing the powertrain. But I would safely assume or say that these are the top specifications or the high level specifications that you would have to probably keep in mind when you actually set out to design an EV powertrain. Okay. So with this, I move on to, I've been talking a lot about feature and we talk a lot about systems. And my entire presentation title today talks about overview of powertrain systems. So it is only important that we understand what do we mean by a system before we actually go into these systems. So what do we mean by a feature? What do we mean by a system? What do we mean by a component? Let's try to understand this briefly. So feature is a customer experience expressed through product behavior. So I go to a shop and I go to buy a two-wheeler for myself, okay? And I say to the shopkeeper, does this come with a traction control system? Okay, so traction control basically manages your slip in slippery conditions, right? So that's the traction control. Does this come with a traction control system? So in this case, traction control is a feature that we are requesting. So feature is something that you can visualize, right, in the vehicle. So that is a feature. So from the feature, we come to a system. What is a system? System offers one or more reusable functions to realize features and generate vehicle behavior. So how would I basically realize this feature? So traction control has to be implemented somehow, and it is implemented through a system. System is a set of components working together with each other to basically generate this behavior. So there would be several components working in unison with each other, finally giving us the traction control feature, right? So that is what is a system. And from system, we come to a component, which is the last final kind of a tangible thing that you can actually put your logic in. Not just your logic, because if you put your logic in something, that becomes a controller, but you have several such uncontrolled hardware also. So everything that you can touch and feel on a vehicle is a component. So a lot of components combined together form these systems, and these systems together basically reflect a feature, right? So I'll just take a very, I already took an example, but maybe something that we can all understand is a cruise control. We all know what a cruise control is. We set a certain speed on our vehicle, and we assume that the vehicle will continue running at that speed without any driver intervention, right? So that's the cruise control. So that is precisely a feature. And next we come to an e-drive system. So which is the system which helps you actually realize this cruise control? That is the drivetrain system, or the e-drivetrain system as you call it. So that is basically the powertrain controller plus a motor controller, your motor, your inverters together, basically they help you realize this cruise control. And then we come to something called a component. What are all the components this system is comprised of? So these are all. So maybe the cruise control input button, even though it's not a big hardware of sorts, but it is still a hardware that is needed to activate that particular feature. So your cruise control button on the steering wheel or whatever, however you activate it, is a component. Your component is the vehicle controller, wherein basically you put your code that when this happens, your motor torque should be set to this target speed, and then accordingly it should be run, right? So your vehicle controller is where you put your logic in. And then comes the motor controller, which is actually motor controller, the inverter controller. That also could be together, but in several cases we have two controllers doing this. And then you have the traction inverters and the traction motors. So these are all the components that make up the e-drivetrain system in this case. This is just to give you an example so that you can correlate what exactly is a feature, system, and a component. So now that we have understood what is a feature, a system, and a component, let's try to deep dive into the major powertrain systems in an electric vehicle. So this is an image of the chassis of the electric Actros, if I'm not wrong. It is one of the e-trucks from Daimler portfolio. So obviously you cannot point out a system at one place. It is a combination of components, but the idea is here to show you where probably the major component of that system lies. So you can see here we have the electrical energy management system, the battery management system, the thermal system, the charging system, the high voltage system, and the e-drivetrain system. So I think a lot of these systems by their names are self-explanatory, but today's session is all about deep diving into each one of them. So with this in mind, let's start with the first one. This diagram that you see here shows a typical route. Again, I'm going back to e-Citaro. E-Citaro would typically take during a day. Okay? It starts from a depot, comes back to a depot. So what does it have to do in a day? Okay? So it starts from the depot with full charge. Your battery is completely charged here. Okay? So then you come and you stop at your first bus stop. Okay? So obviously you've consumed some amount of energy. So your SOC has come down here. And the passengers board here. So assume that you are in a colder climate. Okay? So you've maintained your cabin temperature by turning on the heating. Doors are closed and everything. You stop at the bus stop, you open the doors obviously, so all your cabin conditioning goes for a toss. Again, you have to reconfigure the conditioning, right? So your passengers board, you close the doors and you start again. Again, your energy is consumed. It has gone down because you again need energy to maintain the cabin heating. Again, assume this is a downhill because I see the SOC has gone up. So why does the SOC go up? Because in a downhill you can actually have something called as a recuperation or a regeneration, wherein you basically convert your kinetic energy from the motors back to the electrical energy in the battery. So this is possible in electric vehicles. So again, your SOC has gone up, right? So SOC has gone up, then you stop again, probably at a bus stop where you have a possibility for an opportunity charging. What is this opportunity charging? It is again probably a subset of fast charging wherein you have an opportunity to charge, right? So that's why it's called the opportunity charging. So you just stop for probably a brief 2 minutes, 5 minutes, and it's very fast charging, and so you are able to basically fill up some of your SOC in that brief amount of time. And then you again go uphill, again your SOC goes down, and then so on and so forth, and you come back to the depot at the end of the day. So the idea of showing this image is typically what all are the challenges a vehicle has to face, right? And you see here the range, and here especially the comfort of the passengers in terms of heat is so important that there has to be a system which efficiently caters to distributing energy to all the sources and the sinks. There should be a system which takes care of how much energy is available and how much can I distribute to what component at what point of time. So that is what is an electrical energy management system. So electrical energy management system distributes the electrical energy in a vehicle with the consideration of energy efficiency, the component lifespan, the comfort, and the driving performance. So what it does is, it evaluates how much electrical energy is available to me with all the sources. Obviously, in this case, it would be the HV battery, in case you are not recuperating. Then it will basically calculate, it will see at this point of time what is more important. If comfort, if the energy is enough to basically cater to the requests of all the consumers, then it would recommend it that way. But if there is a situation where a priority has to be given, say comfort would come as the last priority. So if there is a limitation on the traction possible, then you would not probably give as much energy to the HVAC, and you would actually give that energy to the traction instead. So electrical energy management system distributes energy by controlling the electrical power of energy sinks and the energy sources on the HVDC link. Okay, so here you see the different components. It could be different, but the idea is to give you an overview. This is the main controller, the vehicle controller, wherein the logic sits, which decides how much of energy can be distributed to each of these systems. And this is the source, HV battery, the sink being, in case if it's a driving situation, the traction inverter, inverter motor transmission comes together. You have auxiliaries, such as one of the auxiliaries could be a DC-DC converter, one could be a pump for something, one is a charge controller. Not in this case, charge controller will only come if there is a charging situation. So in that case, this will be the source and the others will be the sink. So this is typically how an electrical energy management system would look like, and all of these are the different components in the systems. And what are the main features of this electrical energy management system? Obviously, I already spoke about energy distribution being the main feature. Power limits calculation. So you basically decide how much power can be provided by each of these consumers or sources at any point of time. So you recommend or you limit the power accordingly, and you say, no, you can only give so much of power. It only recommends, it does not actuate it, because it's not a controller to do so. It doesn't finally reflect it in the actual actuator, but it recommends the corresponding local controllers to say, okay, you should limit your power only to so much, and then it can actually accordingly consume or give. And then the third one being auxiliary management, because you also manage the power of the auxiliaries. And fourth being range estimation, because it deals with the electrical energy. It also has a main, range estimation may not be a feature in every electric vehicle, but it is being there in almost all the new vehicles that are coming out. So you estimate how much range is available with the amount of SOC that is left right now, right? So this, in very brief, is what the electrical energy management system is. We go on to the next system. Since I already spoke about cabin conditioning, HVAC, I speak about the thermal management system. Why do we need a thermal management system? It's not only important to maintain the temperature of the cabin, but it's also important to maintain the operating conditions of the components, like the HV battery or the powertrain, in this case, e-motors and the inverters, because they can only perform to their optimum efficiency if they run at a proper operating condition. So the thermal management exactly does that, okay? So what it does is, it basically maintains the temperature of the powertrain components as well as the cabin temperature. So here, if you can see, this is again maybe a block diagram of how a system, thermal management system would look like, with again the logic being in a vehicle controller. Here is where your code will sit in, and it will decide with what, like you basically get the inputs from each of the thermal components, like the coolant pumps or the battery heater or the cabin heater, the radiator fans, the compressors, etc. So these are all the thermal components that are there in an electric vehicle. So you get the operating conditions or the temperature, for example. You get the inputs from the temperature sensors from each of these components. And based on these temperature sensors, you design a logic which decides how much of energy should be given to either heat that component or cool that component. For example, a battery would need heating as much as it will need cooling, depending on the ambient temperature or the current temperature that it has. But possibly powertrain may not need so much of a heating because it has a high operating temperature. So motors can run at a high temperature. So it would possibly need only a cooling, and that too not a very aggressive cooling, and that's why there's not so much emphasis mostly given to the amount of cooling, and you only get done with air cooling also sometimes, and liquid cooling is also not kind of entertained in powertrain, but that's also changing. So, so that's what the vehicle controller is. So the entire logic as to how these temperatures have to be maintained will sit inside the vehicle controller. And obviously you will also get an input from the driver turning on the AC or the heater, telling, no, I want my temperature to be maintained at 25 degrees. So accordingly it will set its logic and produce as much heat energy, or ask the actual actuator to produce so much energy so that you can maintain the cabin temperature at 25 degrees. Okay, so I already spoke about this. So the main features being battery heating cooling, powertrain cooling, and cabin heating and cooling. These are the three main categories in which the thermal management actually functions, right? So that's what is the main feature of a thermal management system. So this is just showing a diagram where it's just taken from internet. So yeah, where possibly different components are placed. So you may not have all these components in every electric vehicle, but there are different ways in which heating or cooling is done. So in some electric vehicles you use a heat pump, in others you don't. You have something called a brake resistor that you use to basically dissipate, store recuperational energy, and then use it as heat later when you actually need it. So that's also done. So there are several ways of actually doing this. Okay. So this is in very brief what a thermal management system is. Then we go on to the battery management system. I think everybody is aware of this. This is possibly the most talked about system, and we know what it is. So this is again the e-Citaro, and so we had the batteries not just on the top, but also in the engine, rear engine bay, because it's a big bus. We had to cater to a big range. So we needed as many battery packs to actually cater to that range. So we had placed some on the top, but some were also in the engine bay where the erstwhile engine used to sit, and we used to take it out and we actually put the batteries there, right? So, so battery management system, obviously as the name says, it is the supervisory system which basically supervises how the HV batteries are functioning, okay? So it is protecting the battery from the operating outside its safe operating area. It monitors its state, calculates and reports its secondary data, and authenticates and balances its environment. This is by definition, but let's understand what does it actually mean. So this is maybe in a very rudimentary way, a battery management system, wherein you can see we have 3 packs of batteries, okay? So every pack would have several number of cells together in series or parallel, okay? And then you would have something called a cell management or a cell supervisory control, which would basically keep sensing the characteristics like voltage, temperature, and current also in some cases. And then you would basically give out this information to the pack level BMS. Every pack will have its own BMS, which would basically balance all the cells in that particular pack. And then together they will be controlled by a master BMS controller, which would basically balance all the packs together. So if there are any imbalances on each of these packs, that would be handled on this master BMS controller. This is how typically it looks like, even in BEG. Now you can decide based on your range requirement or your energy consumption, how many packs would you want in series or parallel to basically give out so much energy, right? And you have a contactor obviously from the HVDC link, which controls the flow of high voltage here. So what are the major features of a battery management system? We understood what does it do, but what tangibly are the features of a battery management system? Be it at a pack level or a master level, it will just extrapolate it to a battery pack, or it will be to a cell level, okay? So SOX estimation, when we say SOX, it could be state of charge, state of health, function, anything. So state of charge estimation using the most, what do you say, the usual way of doing it is through current integration, so we do that. And then we have the state of health, which is you basically determine what is the health of the battery, how is the health of the battery obtained. You can do it through several ways, impedance method, or internal resistance calculation, or you can just count the number of charge-discharge cycles where, with respect to how much it is expected to give over the lifetime, basically balances out all these characteristics so that you don't have different SOCs, different cells having different, or packs having different SOCs at any point of time. And then obviously the contactor control. So when should the contactor actually be closed? When should be opened? When should the high voltage flow actually happen? That is also done by the battery man. So there are n number of features. I'm just enlisting some top few so that you understand what does a battery management system do in an electric vehicle. And now on a very top level, how is a battery pack selected for an electric vehicle, okay? So what we do is we basically do something called as an energy consumption analysis. And for doing an energy consumption analysis, you have to obviously first understand what would be the target range that this particular vehicle has to meet, right? So you need the target range. You can probably also have a drive cycle, so a typical drive cycle where this vehicle would possibly run, right? So you will have those inputs, because if you have a certain route, you know this vehicle is supposed to go through this certain route. It will have an uphill, a downhill, or certain demography, and you have to keep it into account because the energy consumption will be accordingly, right? So traction would involve so much energy, and so on and so forth. And then your vehicle dimensions, the gross weight, and the estimated power consumption from all the other sinks, be it traction, be it auxiliaries, be it the HVAC. So the consumption, estimated power consumption from all this has to be kept in mind, and you do something called as an energy consumption analysis. So you decide that this vehicle, to meet a 150 kilometer or a 200 kilometer range, would typically need, say, so much kilowatt hour of energy, right? And then you decide, okay, so how do I select a battery? So if I have a battery which gives me, say you need a 200 kilowatt hour of energy. You have a battery pack which only can give you 50 kilowatts. So you need 4 of such battery packs, right? So that's how you decide how many batteries would be needed. So this is on a powertrain level. Obviously, you will have several other inputs from a packaging point of view, or even from the cell chemistry. I'm not even talking about the cell chemistry because those are deeper things. I'm talking more from a powertrain perspective, energy consumption side, that how basically a battery would be typically selected for an EV. And we do that. We do that. In the beginning of the project, we actually take all these things, we subject it to an energy consumption analysis, we get a rough estimate. Obviously, it may not be 100%. And we also have to take into account the depth of discharge of a battery. So they may not work for a 0 to 100% SOC. They may have like a 5% to 95% operating zone. And you have to consider all those points, and then you basically decide which battery and how many battery packs in series or parallel have to be connected together to give out so much of energy, right? So this is about the BMS. And then we talk about the e-drivetrain system. I think it's pretty straightforward what e-drivetrain system is. I already mentioned about it in the introductory slide, but it is something that propels the vehicle, right? It gives the power from the battery to the motors. So everything which is involved from giving the power from the battery to the e-motors is the e-drivetrain system, okay? So here you can see there are 2 axle configurations from the Daimler portfolio, this being a hub motor configuration and this being a central motor configuration, wherein, like 2 types, just wanted to show how, this is just an e-axle, but this does not mean this is the complete e-drivetrain, but this is one of the most crucial components of an e-drivetrain, right? Then I explain a little bit more about what an e-drivetrain system here is and what all are the components that actually come together to form this e-drivetrain system, which I already kind of spoke about briefly. So you would have all the driver level inputs coming here in terms of brake pedal, act pedal. You will have a parking brake, that's also important. And then you have the steering control. You have, in some cases, you will have an e-brake lever, several ways in which you can actually do the braking. So all these inputs together will be fed to a controller, vehicle controller plus a motor controller. Together will try to satisfy the demand of the driver, right? If the driver has pressed, say 50% of accelerator pedal, you would have to generate as much torque for basically sufficing that much, right? So that's the drivetrain controller's key responsibility to do that. and then it translates that into the traction inverter and the motor and the transmission. So this is the e-drivetrain system. The main features, like I already spoke about, torque demand calculation and distribution to the wheels based on the driver demand, and then the regeneration in cases there is a braking scenario, right? So you again take the energy back from the motors and give it back to the battery. So this is regeneration. This is also the main function of e-drivetrain. Component protection, obviously the drive controller always makes sure that you are abiding by all the overspeed limits, over voltage limit, over current limits, and then it has to produce the torque to be able to abide by all those limits, right? So that's what is also one of the key responsibilities of the drivetrain controller. And then you come to other driver-independent torque assist features. So in several cases, driver may not even intervene, but the drivetrain controller has to intelligently decide that I have to give so much torque. For example, your drivetrain has failed, and you have to come to like a service lane or some sorts, and you all must be aware of the limp home feature, wherein the drivetrain controller would itself decide, okay, let me give a reduced torque of X by 10% or whatever, X being the maximum torque, and then that much will be commanded to the drivetrain so that it is just enough so that it can come to a service lane and then you can actually get it serviced, right? So that's a driver independent feature. And similarly, you have something called a creep assist, hill assist. These are features wherein probably driver has no intervention, but then drivetrain controller itself has a logic inside where it decides, look, I'm on a hill, I'm about to roll back. I have to give enough torque so that I don't roll back the hill. I have to keep going up or at least stay on a standstill position. So that's a hill assist feature. That's what I just explained. Creep feature being something synonymous to maybe idling on a conventional vehicle, wherein it's not really idling, but something synonymous wherein you just give a very brief amount of torque and you just keep moving with a very minimal speed. Because you have an e-motor, you could as well do that. You don't have an engine. So the creep is again a torque driver independent feature. Then you have many safety features like I already spoke about. So these are main features of an e-drivetrain system. And what are typically, again, I think everybody may already assume what would be the key factors that we would have to keep into account, at least from a high-level powertrain perspective to design an e-motor would be, we have to know what would be the max speed we want the vehicle to be running at. I want this vehicle to be running at 12,000 RPM max, okay? So I would be giving that as a max speed to be able to choose a motor for this particular thing. The voltage specification, even though my vehicle is at 800 volts, what would my e-motor be? It may not be at 800 volt, it could still be a 400 or 500 volt, and then you would have to have a DC-DC converter accordingly or whatever, right? So a voltage would be another input. The torque power requirement based on the application, basically the application. So if it's a heavy duty kind of application or so you have a crane application of sort, or you have, it's a truck kind of application, you would need heavy torque, heavy power. You may not as well be concerned about how is it going to that location, right? So you are as well concerned about how is it able to perform there, right? So how much torque and power it is able to give. So that is the application point of view which is going to decide the e-motor. Then the size, because on a vehicle you have a limited size that is available to place all these components, right? So size plays a huge role in deciding what kind of an e-motor would give. Some e-motors may be very suitable but may be very hefty, may be very big in size, and you may not even accommodate, you may not be able to accommodate it on the vehicle. So size is a very big input. And then obviously the e-axle configuration, I just showed you in the previous slide, the two types of e-axle configurations. There are many such other configurations possible. So you have to decide basically how and which kind of e-axle would be most suitable for this kind of a vehicle application, right? So this being the e-drivetrain system. I would move to the next one, being the high voltage system. This is often not talked about so much, and you would not find too much of internet details about a high voltage system. But we always talk about high voltage, and we know at what levels do electric vehicles actually operate. The passenger cars typically operate around 400, 500 volt, but commercial vehicles actually go up to 1000 volt, like I just mentioned. So there are such high voltages you are dealing with. So it's only important that you have a system which monitors the safety of not only the user, but also the components in this high voltage operating scenario, right? So you need a system which takes care of that. Who is taking care of that? None of the systems that I spoke about is taking care of the high voltage application, right? So high voltage application, according to me, is probably one of the the most important system in an electric vehicle design, which is often not spoken about. So what is the high voltage system responsible for? It's not only responsible for distributing the actual HV power, but also regulating the safety of the components as well as the user during the operation. So this is a very, what do you say, a simplistic flow of how the high voltage would flow in different components, starting from, say, the battery, inverter motor, the charger charging the battery through the charge port. Then you have a converter, this black line being the low voltage connection, so this is not a high voltage connection. So converter and then the accessories, basically. No, the HV battery will basically DC-DC converter, and then this will be a low voltage. I think this will be a high voltage. So this is the high voltage system. And what are the main functions? What is this high voltage system? What does it do, right? So if you see here, this is a block diagram which talks about probably most of the components of a high voltage system. The HV battery at its core. You would have a power distribution box which takes care of basically distributing the power, HV power, to all the HV components. It is synonymous to a fuse box probably in an LV network. But yeah, so something like that. And you would have different HV components, the axle, the DC-DC converter. You would have the onboard charger in case of AC charging, DC-DC converters, water pump, coolants, etc., etc. So you would coolant walls, etc., etc. So all the distribution would happen through a power distribution box. And this is a typical HV architecture for a very simplistic architecture. Obviously, the HV architecture differs from vehicle to vehicle, and there have to be several points that have to be kept in mind while designing this HV architecture. So the main features of this HV system are not just the HV power distribution which I spoke about, but probably the most important one is activation and deactivation of high voltage power net. So when you basically crank the engine, you do not expect the high voltage to just turn on, right? So there has to be a system which takes care of certain steps before you actually turn on the high voltage, right? Some certain safety steps have to be taken. For example, you have to you have to use a pre-charge resistor to actually pre-charge the HV intermediate circuit so that there is no inrush current available to the capacitive loads and they don't actually break down, right? So similarly, there has to be isolation that we were just speaking about. So isolation is a very important feature of HV, wherein you basically isolate the high voltage from the low voltage using an isolation resistance, and you have to always measure the resistance of this isolation resistor and ensure that it is above a certain value, right? So if it goes below a certain value, you are at risk of high voltage being leaked into the low voltage. So at that time, you do not even let the HV go on. So these are all the checks you do even before the HV is turned on, after the driver actually cranks the engine, right? And similarly, you have something called a high voltage interlock. What does this do? So a high voltage interlock is like an LV line running through all the HV components. It's like a low voltage line running through. So it basically checks the integrity of the continuity of all the components. So if there's a break in the LV line anywhere, so basically you are again at a risk. So what it does, it doesn't let you turn on the HV, right? So this is what the HV interlock system does. And then you also have something called an active discharge. I think everybody might be aware what is this. So whenever HV is turned off, so you have to make sure that the remaining high voltage is actually discharged through some means, usually through a resistor or any sort. So it also does this, right? So these are the main features of a high voltage system. Basically, it all has to do with the safety of the components and the user. Okay. I come to the charging system. I think this has been deeply talked about in the last slide. I don't want to probably reiterate here because I think we already spoke about level 1, 2, and 3 kind of charging. So obviously, I told you this is one of the important factors that help us decide, design an EV. So if a DC and AC charging both is required, then you have to accommodate an additional onboard charger if an AC charging has to be needed. But if you don't need an AC charging, then you don't need an onboard charger. So you just have a DC infrastructure to take care of it. So range anxiety is definitely one of the key things that drives an electric vehicle, and that's why many people are like a little reluctant to even buy electric vehicles apart from its cost, obviously. So that is why it's very important, and there are a lot of innovations that are happening in this area. I think Professor just spoke about some innovations in bidirectional charging and integrated charging, and even Daimler is doing a lot about utilizing traction inverters just for charging. There are a lot of things happening in the same area. So, so a lot of scope of innovation and development in this, and that is why charging system is definitely very important. And to design an optimum charging system is even more important. Okay, so I have shown a charging system, a very simplistic charging system wherein you only have DC and AC. I have not shown other sources, so you have like a pantograph kind of charging, you have inductive charging, others. So this is only a conductive charging that I've shown here, wherein you typically have a charging point, you have a charging inlet which talks to something called an EV communication controller. So EV communication controller, it takes care of all the interfacing between the vehicle and the charge station. And then you have something called a DC charge box, that is where the charging contactors are placed, which is then connected to the battery. So this is the high voltage network which is shown through the orange line. So in case of an AC charging, your current would flow here, onboard charger would convert it into a DC, then it will get then the battery would be charged accordingly. And in case of a DC charging, you would not need an OBC, and directly through the EV communication, directly through the inlet, you can actually connect through the battery on the high voltage line. So EV communication controller takes care of all the communication between the charging, as I already mentioned. So everything with respect to when the charging, so the charge controller is the main vehicle controller kind of thing, which has all the features like when the charging should start. In case the charging starts, you should not allow the traction to be on, like he just mentioned. We make sure that there is no torque on the motors, and that's precisely, there is a controller who does that, right? So it immobilizes the vehicle if you detect a charge plug, right? So that's precisely the feature of the charge controller. And then you have something called lock detection, unlock detection, wherein you plug the charger and then you really make sure that the charger is locked. Otherwise, if if it's half there is a possibility of HV arcing if there is a small space left, right? So you have to ensure that there is a proper motor. There is a proper motor in the charging inlet, so you have to ensure that there is a locking sequence that is done. So who takes care of that? There has to be a controller who does that, right? And charge controller takes care of all of that. So this is typically the different components in a charging system. I already spoke about the major features through this, and obviously to decide what kind of charger would be needed, we would know what kind of charging, we would need to know what is the battery capacity of this vehicle, we would need to know what is the maximum charging current that the battery can accommodate, right? So accordingly you can design the charge. And obviously, so depending on the application, if you have a liberty of overnight charging, you may as well choose obviously slow charging, but if you don't have that, you will have to take care of the maximum charging time as well, right? So all of this takes into account how a charger is basically designed. So with this, I end the basic. There are many other systems in an electric vehicle. I have not talked about the fuel cell system here because that's not probably the most, these are there in every electric vehicle. So there are other, there is an auxiliary management system, you have fuel cell management system, you have a tank control system in case of a fuel cell. So I've not spoken about that, but I've tried to just show what are the main systems which every EV would have, irrespective of whether you have a small truck or a small bus or a passenger car, right? So that's how it is. Now, I kept on talking about the controller and the implementation of logic in that controller, right? So what we do, sure. I'll just have one more slide after this, that's it. So I wanted to give you a brief about how the controls are basically designed and then integrated onto these controllers, right? So that's what we do, right? So what we do is, typically we have, I already spoke about features. So we have a typical feature in front of us. For example, let me take an example of traction control again. So we wanted to design and develop a traction control system or a feature for the electric vehicle. So we have a high level feature requirement. We know what this traction control is supposed to do. So we write a high level system specifications for this feature. So we just write, in case of traction control, if there is a low friction kind of a situation, if there's a friction, low mu kind of a situation, in that case, the motor should be able to stabilize the vehicle. There has to be, the torque has to be regulated in such a way that you don't actually slip out of that situation. You are able to maintain the integrity of the vehicle, stability of the vehicle, right? So you write the high level system specifications, and then you actually write the component level specifications. So each of the components that actually formed that system the e-drivetrain system in this case for the traction control would have a role to play, right? So for every component you would decide what should the motor do, what should the inverter do, what should the controller do, and you write the component specification. And then you basically code it. So we typically in automotive world, we use something called a model-based coding or a model-based programming. We don't use handwritten codes because of its known issues. We have a lot of issues with handwritten code. So we use MATLAB or model-based coding for actually writing the code. And then we embed it onto the controller, right? So we put it onto the controller and we test this controller not only on the component level, but then also on the system level. We first only test the component, then we combine all these components together and then we see how the system behaves, and then we put the system onto the vehicle and we basically test how the vehicle testing would happen. And typically this traction control was something that you could relate in the first video, which we also did in Rovaniemi, where we checked how the traction control actually behaved. So that was what is the vehicle testing. That's how it culminates the entire thing. So this is what our team at DTICI is majorly involved in, from feature development for the controllers, right? Apart from all the component selections and all that. So after this, I just wanted to briefly touch upon another aspect, a very key aspect of how we culminate, how we see whatever we have developed in a vehicle, right? So we have something called a fleet monitoring. So if you see here, it's an extended V cycle. So an extension of the V cycle called a fleet monitoring, right? So in this case, what we do is after the code is actually integrated onto the vehicle and your fleets are actually running on the road, we have a mechanism where all the data from each of these vehicles is actually stored in a data logger, through a data logger and sent to the back end. And we get back this data and we keep analyzing this data for different systems. And the reason for analyzing is why we evaluate the quality of the controls, first of all. How is it behaving? Okay, it's one thing to test it in a vehicle test situation, but then how does it actually run in a fleet over a long period of time, on and off, on and off? There may be many issues that come, which we may not even have predicted before. So we keep evaluating the quality of the controls and then keep modifying the software and have like batch updates, like you have like your phone update coming, iPhones, whatever update coming. So similarly, we have batch updates which we keep pushing. So it's all electronic. That's the power of electronics. You can always push your updates from backend, right? So that's what we do. We keep evaluating this. We also check this data for the performance of the vehicle. So state of health, for example, we keep checking how the battery is degrading and at what point of time can we, and we also estimate, say, the warranty of a particular component through these kind of data. We say the battery would probably last 10 years. So after 10 years, you would have to change it. So these are the things we also provide to the customer, saying we always write it in the sale, whenever we sell it to the vehicle, that, okay, the battery would have to be changed probably after 10 years. So how do we decide all this? This is by doing things like this. And then obviously root cause identification of issues and predictive maintenance. So predictive maintenance being before a component is going to go bad, we already detect it through some ways. So these data, these continuous data will help us hint all of those things, right? So this is an important step which our team also at DTICI does, is we culminate whatever we do with the fleet monitoring and assess the quality of the software that we do. And finally, how the EV is actually behaving, right? So with this, I would like to end my presentation, and any questions?
One of the slides showed the battery placements on the top.
Yeah, roof.
Was it intentional? What are the thermal implications if you get such placement in India?
Yeah, that was intentional because every vehicle has its own specifications. So this vehicle did not have too much, we did not have a possibility to actually put it onto the ground, which is generally the case. You generally have like, what do you call it? You generally have it on the chassis, the floor mounted batteries, which was not the case here, because the weight of the batteries was too much. So you had to accommodate for it. And thermal implications, not as much. We did not have too many thermal implications, but as I mentioned, there had to be a balance between the number of batteries that were placed on the top and the rear engine bay. So we had many variants of the buses which came out with 10 battery packs or 6 battery packs or 5, depending on the range. So we had to balance the number of battery packs. So if it was a 6 battery pack, we had to put, like for example, we put 2 battery packs on the top and probably 4 at the bottom. So we had to do a proper structural analysis and then stability analysis of what this would mean if we basically put so much weight at different areas.
So another question attached to that is when you have a liquid cooled battery pack, for example, or with heating capability. So placing batteries like this, that means you have to take a design choice to disassociate the cooling and heating systems from a central thing to a more modular structure.
Yes.
So that was
wiring in many cases may also become quite big, right? So you have to, the thermal components may be somewhere, but you have to basically, there has to be a trade-off between certain things. I'm not sure where exactly was the thermal cooling, thermal components placed here. I'm not exactly sure, but obviously keeping in view the size of the vehicle, that may not be so much of a concern, right? So because so you design it accordingly. But in many cases, what we do is we also optimize. So the same compressor which is used for actually cooling the battery may also be used for cooling the cabin. So you also take some choices there. So you also optimize your thermal circuitry is a very important role. So once you decide the thermal circuitry, that's one important aspect you have to keep in mind when designing a thermal system, and that also decides basically the placement of the batteries.
Madam, as we know that in the battery pack, it consists of number of cells, right? So in the cell, in the battery pack, it consists of number of cells. It may be in series or parallel. So to monitor the temperature, how you are placing the sensors? Means individual cell you are placing, or how you are placing
every
the sensor?
Cell will have a sensor.
Every cell will have sensor.
Every cell will
so what type of sensor you are using in industry?
I'm not sure of the details.
Not sure.
No,
and
sure.
second question is that with regard to battery pack manufacturing, while we are manufacturing the pack, so how we are selecting the number of cells? Because each cell will have different characterization.
Correct.
When you are getting, so how you are doing the grading?
No, we don't, because we don't create a battery pack of our own. We generally select a battery pack which is already available with the supplier, right? So after doing the energy consumption analysis, we choose the best available battery pack that is already there. And the cell characterization and everything is done by the supplier itself, and we have a battery pack that is available, say from Samsung we have a battery pack, or CATL is a very big company which gives battery packs, right? So you already take the battery packs from there, wherein you basically ensure that this is the best possible battery pack probably that you can get for your kind of an application. So we don't actually do the cell characterization in-house.
Ma'am, in the last slide you showed about, in the last slide you showed a preventive maintenance feature in the vehicles that you do. So is it just like in the IC vehicle or the internal combustion engines, we have a kilometer-based preventive maintenance. Is it the same, or is it some other?
Predictive maintenance is a very open term. It could be anything. Wherever you predictively can maintain a component, that is predictive maintenance, right? Wherever you can already estimate the degradation of a component and take steps to ensure that it doesn't fall out, right? And that is predictive maintenance. So in case of e-motors, you would already see if the e-motor is getting degraded and eventually it will run out of life, right? And you have, or probably you will have to service it or replace it. So you will have to basically analyze certain characteristics of this e-motor to be able to replace or service it at a certain amount of time, right? So that is predictive maintenance. Predictive maintenance could also be for the batteries, wherein, like I told you, you already check the state of health of the battery, how are the charge and discharge limits changing over time, and these are the certain things. So you have predictive maintenance of every component, but then you decide for which components do you really want to do predictive maintenance and what would make sense, right? So motors and batteries probably are the two main important ones for which you would do predictive maintenance. So yeah.
Hello. Thank you. My question is related to the various features you take into account right at the beginning. One thing I did not find is about roadmap, and I have a question in this. For example, battery size, range being larger, the battery size is also large. In that context, green hydrogen could be a possibility. Does it also come in your innovation plan, which is a roadmap? And that also related to the cost, whether customers are related to pay that amount of cost, what is the amount of cost, especially comes from the battery design.
Yeah, so battery is typically the most expensive part in an electric vehicle, right? So that is why a lot of emphasis is happening in the amount of innovation happening possibly in battery chemistry. I don't think that kind of innovation is happening anywhere else, because there is a need for more and more range, and you cannot keep increasing battery packs to meet that kind of a range because it has an effect on your energy efficiency, right? So a lot of innovation is happening on the battery chemistry. So as an OEM, we are also looking at different chemistries of a battery, right? Solid state batteries, et cetera, et cetera. So we are looking at different products are being developed with different kinds of batteries, and we see how they are actually performing, right? So you said hydrogen, right?
Yes,
fuel cell.
hydrogen.
So we already have a product which is going to release this year. I was already talking to professor here that we have hydrogen fuel cell based, same e-citaro with hydrogen fuel cell as a secondary source, but it is only acting as a range extender. So because hydrogen fuel cell itself has its inherent limitations, you cannot use it as a primary source of fuel right now. At least it's not at a state where you can. So battery is still the primary source, and you use hydrogen wherever possible. You have a proper algorithm that takes care where should the fuel cell kick in, at what situation should the fuel cell. So at least it can basically increase the range by say 20 odd kilometers or 50, depending on the size of or the amount of hydrogen fuel mixture that you are actually using. Right? So we are already using, we are already creating fuel
Another
cell.
question, as a OEM, you have your own design, especially the body part, and which maybe you're outsourcing. So those people are finding very difficult to supply specific to particular customers or OEM. Keeping that in mind, your body design, how it is taken to account, keeping the ecosystem, the other supplier into account?
Actually, the body design also changes from the vehicle to vehicle, right? So every vehicle has its own body design. So there are several variants of a vehicle for a certain platform that are released, but then I would say it's always ensured there are many suppliers out in the market. For example, if you have to even choose the batteries and you want the batteries to fit in a certain frame, you would have to look at a certain dimension of the batteries. Obviously, that reduces the number of suppliers that you would probably have. But then there is also a lot of parallel development happening in-house, not just for batteries, but also for powertrain components. So we're also doing that. But I think powertrain suppliers are very aware of the major OEMs and the kind of structures or designs they come up with. And so a lot of their major products are actually designed so that they can accommodate most of these products. That's how.
What is the target customer revenue you are targeting? Serviceable TAM, total obtainable market, and serviceable obtainable market. How much of the total market you are going to capture in your design phase, keeping that in mind?
The Indian market, you're saying?
Yes.
Right now, this is not for Indian market. We have a sister company called Bharat Benz. I think you're aware of that. So Bharat Benz caters to the Indian market. So that is completely for the Indian market. But DTICI is only for the European and the US market as of now, and the Japanese. Yeah.